Hello guys, so today we're going to be discussing the solution to Inpho 2013 problem 7, which is about the Brunt-Vaisala oscillations, and it's a nice problem and there are many parts to it, so expect this video to be slightly long, especially since this is one of the harder problems in Inpho. So anyways, we're going to go at this one step at a time. So it's part A, and we had to derive the adiabatic lapse rate. So first give a read about the beginnings of the problems, take time, pause the video, and maybe give an attempt for part A, and when you're done, go back and resume the video. This is an interactive video, so that stuff should be done. Alright, so we had to derive the adiabatic lapse rate, which is given as gamma is equal to dt dz, where dz is the height. So consider a coordinate axis like this. The c is going to be here, and you can say x and y. So it's going to be the vertical distance that the balloon is moving on. So the first thing that we have to note is that it's an adiabatic process. So in adiabatic processes, we always know that Tv to the power of gamma minus 1 is equal to a constant. And coincidentally, since PV is proportional to T for an ideal gas, and we're assuming that this is an ideal gas here, that means that P to the power of 1 minus gamma times T to the power of gamma is equal to a constant. And gamma in this case is the adiabatic constant, which is the constant pressure heat capacity over constant volume heat capacity. So let me just make this another color just for visual sake. Yeah, red seems nice. This is going to be one of our main things that we need to know in this solution. Alright, another thing. Let's consider a small strip in the atmosphere that is cylindrical like this, and it has a very small width of dz. We're going to say that there's forces of gravity that are acting on this small cross-section of the atmosphere. And we're going to say because of this, the pressure on it is going to be the mass times the height. So it will be dp is equal to negative rho g dz. And rho is just going to be density of this cross-section, which we assume to be approximately uniform because this width of the cross-section is very small, so there's not going to be any changes in pressure for that part of the atmosphere. The next thing to note is that by ideal gas law, we know that P is equal to nkBT, where a kb is the Boltzmann's constant and n is the number of moles in the system. Coincidentally, if m is the mass of one molecule that's in the atmosphere, then the density is equal to the density is equal to nm, where n is again the number of moles in the system. So if we say this, then that means that rho itself is going to be equal to mp over kbt. So going back, if we divide, we have these two differentials, we can say that dp dz is equal to negative rho g, and rho again is mp over kbt, so this is also equal to negative mp over kb t, and g is there going to be there too. Alright, so this is a nice start, and because of this we also know that dp over p times t is equal to negative mg over kb dz. So you may be wondering why I wrote this like this, but it'll come clear to you once I write the next thing. So remember that I said p to the power of 1 minus gamma times t to the power of gamma is a constant. So if we differentiate this, we know that 1 minus gamma times dp over p plus gamma dt over t is going to be constant. No, it's going to be 0 upon differentiating. So because of this, we can now go back into this equation and we can substitute dp over p with what we got, and so we can do that right now. Let me copy and paste this equation. So these are two equations that we currently have. So we write negative mg over kb t times 1 minus gamma dz plus, actually wait, we can do this a bit more neatly. Let us write dp over p is equal to negative gamma over 1 minus gamma dt over t, which implies that t dp over p is equal to negative gamma over 1 minus gamma dt. So we know that this and we have this. So these are two equivalent expressions that we have, and we can now equate negative mg over kb dz with this. So negative mg over kb dz is equal to negative gamma over 1 minus gamma dt. So note that once again we have these two over here, which means that the temperature gradient, the adiabatic lapse rate, will be equal to negative gamma minus 1 over gamma times mg over kb. And that is what capital gamma, or the adiabatic slabs rate, is supposed to represent. So we have derived it